Welcome everyone to today's seminar. I'd like to start by introducing our seminar speaker today, Olivia. She's a master's student in geography at Carleton University under the supervision of Stefan Gruber. Her research focuses on analyzing ground temperature observations to reveal changes in permafrost. Outside of research, you can find her playing bananagrams, baking sweet treats, and enjoying the great outdoors. Whenever you're ready.
Thanks, Gabe, for your introduction. I'm really happy to be giving this talk finally. And yeah, my name's Olivia, like Gabriel said. I'm working under the supervision of Stefan Gruber at Carleton University. I'm also working in close partnership with Nick Brown, who's the PermafrostNet data scientist. I'm sure a lot of you have, had the chance to cross paths with him. So today I'll be talking to you about how we can learn more about permafrost thaw in Canada from borehole temperature observations. Before I go into this a little bit, I want to tell you more about permafrost monitoring in a global context. And so permafrost has been established as an essential climate variable by the Global Climate Observing System, which is part of the World Meteorological Organization. So this means that they've deemed permafrost as needing regular, long-term, and spatially diverse observations to characterize both permafrost as well as climate. And so within this ECV title, there are three products or three metrics that have been used to monitor changes to permafrost as well as to the climate. And so these are permafrost temperature, active layer thickness, and then more recently, rock glacier velocity was added. I should add that there are more metrics that are used to characterize changes to permafrost, more ways that permafrost can be observed outside of these three here. But today I'll really be talking to you about the first one, and I'll be talking to you in general about ground temperature monitoring, permafrost monitoring, and then how permafrost temperature fits into this. So, what do we mean by permafrost thermal monitoring, ground temperature monitoring? There are a number of different ways to measure ground temperature. The most common is in boreholes. So on the left image here, you see the top of a borehole, so the casing on the surface portion of the borehole. And on the right, you have this schematic representation of what this looks like. And so once the ground has been drilled into, a tube can be inserted and a thermistor cable can be lowered into it. And this thermistor cable will have different sensors on it, and each of these sensors records temperature or measures temperature, and then this is recorded by a logger. And in recent years, as technology advances, most of these measurements are recorded automatically, and this provides these fairly continuous time series of ground temperature at these, installed sensor depths. And so in this image here, you see sensors are located in the active layer as well as within the permafrost layer as well. Now, although temperatures are recorded at multiple depths, typically when we say permafrost temperature, we mean mean annual ground temperature near the depth or at the depth of zero annual amplitude. So I've added two time series to this image here on the right. And so you can see one is the output from a sensor in the active layer, and the other is from a sensor deep within the permafrost layer. Both of these are on the same scale, so you can assume that the y-axis would be the same across both of these, but you'll notice that there's a very different signal that's produced at each of these sensors. And this is because the deeper you are in the soil, the less sensitive it is to air temperature, which leads to a dampening effect on the sinusoidal temperature variation. And so this is really how the depth of zero annual amplitude is defined, which is where the seasonal variation is less than 0.2 degrees Celsius. And the reason that this depth is chosen is because of this reduced sensitivity, but also because it provides insight into past climates and how climate is impacting permafrost temperature. And so ground temperature measurements across the soil column are used for a variety of purposes, and I've listed just a couple here. So in the first case, they can be used to inform modeling studies. You'll see this in the bottom figure here, where observations in black from a site near Inuvik along the ITH are compared to simulated outputs of ground temperature. As I've said, permafrost temperatures, ground temperatures, are used as indicators of climate and permafrost change. So mean annual ground temperatures at the depth of zero annual amplitude have allowed for really nice summaries of permafrost change across Canada. This figure on the right is from a recent publication by Sharon Smith at the GSC, as well as her associates, that show how mean annual ground temperature has evolved at select sites in Canada. You'll notice in parentheses right next to the names of these sites are the depths at which this ground temperature is reported. And you'll see that in most cases, they're quite deep, 10 meters or deeper, but at some they are shallower. We can see also that across most of these sites, there's this increase in temperature. And observing these changes and reporting on these changes and summarizing permafrost temperature in Canada is really thanks to these tireless monitoring efforts that date back to the 70s at some of these sites. And so overall, we have this nice picture of how permafrost is changing. But if you were, for instance, to zoom in and take a snapshot of these sites, you might notice that within a period, temperature does vary. And this is just thinking of like weather versus climate, how short-term climate can also impact your ground temperature response. And it might differ from the overall pattern of change. But overall here, you see that permafrost temperature is warming in Canada. Again, you can look at the spatial variations and warming rates across different permafrost and climate zones. So this figure is also from that same paper by Smith et al. In certain regions or at certain sites, you can see that there can be up to 1 degree of warming across a decade, whereas at other sites, there's only a fraction a degree of warming. And so permafrost temperatures have been compared to air temperature, which does explain some of the spatial variability in the observed warming rates. But there are a number of other factors that influence the thermal regime, ice content, soil properties, surface characteristics, and they also influence how the ground responds to warming climate. And so this really brings us into some of the disadvantages of using mean annual ground temperature as a metric when you're interested in knowing how permafrost is thawing. And so these disadvantages are often acknowledged, this isn't anything new. And in the first case, the first limitation of mean annual ground temperature is that the interpretation is confounded by phase change. So if we look at this figure again, you'll notice that at the warmer borehole sites, so again, the y-axis here is temperature, so near to 0 degrees, the slopes that you see are reduced relative to those that are in colder permafrost. And this is often attributed to the loss of ice in the ground, but it never is really confirmed in these types of papers or these types of summaries. And so the reduction in a trend might be because ice is melting, but it isn't necessarily the case. The next disadvantage is that the magnitude at the reported depth is influenced by the depth itself, as well as the terrain characteristics. And this makes comparisons of these values of these trends difficult across all these different sites. And lastly, the changes that are observed across the soil column are not uniform. The ground isn't homogeneous. And so changes at the depth of 0 annual amplitude might not reflect changes that you see shallower in the soil profile. And so this using one sensor leads to a reduction in the information that could be pertinent and useful to characterizing permafrost change. Another way that it reduces the amount of data that we have or the data that we can use is that a lot of boreholes are shallow and don't reach the depth of 0 annual amplitude, and so they're often omitted from analyses. So to summarize kind of what I've just said, that although using permafrost temperature as a metric might be the right call for national climate assessment, it may not be enough if we want to understand local changes to permafrost, especially permafrost thaw. So here we put forward that to learn more about permafrost thaw, we have to maximize the data that's available to us. First, by using metrics that complement the mean annual ground temperature at the depth of 0 annual amplitude. And these metrics should make better use of all the sensors that we have available to us. And then another way to maximize the data is by reporting on as many boreholes as we can, because again, we're interested in knowing where permafrost thaw is happening. So before I get into the nitty-gritty of this project and what I've been working on, I want to talk to you generally about how this project was conceived. So this master's project is part of theme 2 of PermafrostNet, which is to do with monitoring of permafrost change. It was initially proposed as a PhD project, and then later was split into 2 parts. And Nick Brown, who I've already mentioned, he's a PermafrostNet data scientist, he undertook the first part, which was to develop and test metrics using simulated data that resembles observations. And then in my part for my master's project, I've been evaluating how these metrics work on actual observations and then using these metric results to characterize change in Canada. I'll tell you a little bit more about what Nick did without going too much into detail. So he ran a number of simulations that lasted up to 120 years. He looked at different ground characteristic scenarios, how much ice is present in the ground, ice content, is there excess ice or none, as well as different like climate scenarios. So in some simulations, he applied a warming trend. His simulated outputs that were relevant to the study were ground temperature over these 120 years, liquid water and ice contents, as well as sensible and latent heat. He then derived a number of metrics that comes either directly out or is derived from the data, and was able to evaluate the strength of the relationship between the model outputs as well as the metrics. So comparing, how well these metrics reveal sensible and latent heat in the ground. Overall, he was able to recommend a complementary set of metrics that best explain heat gains in permafrost and best tell us about permafrost thaw. In part two, it's really started with this borehole temperature data compilation, and then based on the recommendations by Nick from part one, was to adapt these metrics to observations. Observations are not this idealized case like simulations are, and so a number of alterations had to be made for them. And then really to understand, what the limitations are when we apply the metrics to the observations, as well as then provide insight into changes to permafrost in Canada. So this project relied on a large borehole temperature data set to really see what these metrics look like across a range of sites in Canada. And this is where I give thanks to all the contributors, everyone who pointed us in a direction, showed us where their data could be found, provided us with updates, provided us with completely new sites. And it's really thanks to them, thanks to their time that they dedicated to publishing this data in the past, that this project is possible. So we were able to overall accumulate over 100 sites, and these are found on different servers. The Northwest Territories Geological Survey has an open publication database. The Yukon Geological Survey has one too. Nordic Canada is another great source of data here. And then, of course, there's just a number of different publications within each of these servers that contribute to the total borehole temperature data set. So this is where the boreholes are found in Canada. They're located in a variety of terrain. And here the data set includes every single borehole, regardless of its site characteristics. We've only chosen to split them up based on whether or not a disturbance was noted near or at the site. Mainly human disturbance here, like in the middle of a road, near a road, in someone's backyard, or in more natural terrain. We have a lot of boreholes in the Yukon here. You can see this map may make it seem like they have a greater spatial coverage, but it's really just because a lot of the boreholes are located kind of like on top of each other within a few meters or kilometers of each other. And so for visual purposes, they've been expanded here. One of our requirements was that there needed to be at least 5 years of data. And this is because we were interested in looking at trends. And so we wanted 5+ years of valid data. Many of these sites only have 5 years. They were more recently drilled and instrumented, but some go back as much as 20 years. Our depth requirements, well, there were none. We accepted boreholes that were shallow as well as very deep. Here's what the depths look like. So here's a graphical representation of our sensor depth, where every vertical line is a different borehole and every square is a different sensor. So there's temperature being measured at every sensor here. So what you might notice is that some of them are quite deep. Most of them have data extending to about 10 meters depth, but some of them are really quite shallow and don't even make it to 5 meters. But we can still include them. We want to still include them because permafrost, isn't just at sites with deeper boreholes. And there's still important information that we can derive from the shallower boreholes. And this information that I speak about is really represented through metrics. And so I'm going to spend some time talking about each of these metrics. And so these stem directly from the data or derived from the data. And like I said before, were suggested or recommended based on the results of the first part of this project. So I've grouped the first two metrics together. Before I tell you a little bit more about them, I'll just take you through the figure here. And so again, you've seen the borehole drawing on the left-hand side here with the important layers in the ground. On the right here, many of you have probably seen a trumpet curve. In case you haven't, the line in gray here shows the mean annual ground temperature at the sensor depths. The orange line on the right here is the maximum annual temperature curve at these sensor depths, and the blue is the minimum annual temperature curve. And this is often used to just describe data at a site. So mean annual ground temperature, I've already spoken about, is the ground temperature deeper in the ground, whereas mean annual ground surface temperature is, as the name suggests, near the surface. And we include surface as well as deeper ground temperature measurements because the surface is more sensitive to short-term changes to the surface temperature. And so it provides a different picture of changes in the ground. I just showed this figure. Now there are orange boxes that are highlighted here. And these boxes correspond to where the depth of zero annual amplitude is at the site. So you'll notice that they really vary from site to site. And because of this, it makes comparing the values at these sites difficult because they are, some might be around 2.5 meters deep, some can be as deep as 25 meters. And so acknowledging this, we've chosen a fixed depth. So we've chosen to look at mean annual ground temperature in the deeper boreholes around 10 meters, and the shallower ones around 3 meters deep. Similarly, mean annual ground temperature are the sensors about up to 30 centimeters deep into the ground. And so at some sites, if they don't have shallower sensors, they just are the metric MAGT won't be computed at that site. Next, we have the top of permafrost. This metric is really nice because it provides a more physical explanation of permafrost degradation. You may think of it as similar to the active layer thickness, but there are important ways to distinguish it. First, it is a measurement of depth, not of thickness, and so it's measured relative to a stable datum. That means that in the event that there is surface subsidence, thaw settlement, the top of permafrost won't be underestimated, like active layer thickness might. Top of permafrost is interpolated between a sensor in the active layer and a sensor in the permafrost table. And so another benefit of this is that in the field, you might not be able to probe a ground if you're in bedrock or in coarser materials, but because it's interpolated, you're able to still estimate the depth of the permafrost table. Lastly, in the event that a super permafrost talc forms, you can still compute the top of permafrost, but you couldn't, for instance, probe the ground because of the presence of a talc. There are a couple of considerations when analyzing the top of permafrost values. So here we see top for 2 sites in Nunavik. The blue bars are the estimated depth or the estimated tops of permafrost. The error bars aren't error bars necessarily. They're the sensors, the depth of the sensors used during that interpolation. And you'll notice that there's a good distance between the 2 sensors at these sites that are used to estimate top. And so what's good to remember here is that in the event that a sensor fails in a year, then different sensors will be used during interpolation. And this can sometimes skew the results. And so you'll notice here, the years that I've circled, the tops have jumped, quite a bit lower than their surrounding values. And this, you can also see that the sensors used during that interpolation have also changed. And this was because the sensors from the years before had failed. And so what you see here might seem like an increase in the top of permafrost, but it is in fact just because different sensors are used. So it's important to, keep this in mind I kept this in mind when computing top at all these sites. And I went in and checked, why there might be certain changes like this over time. The first metric is called thermal integral. What it is a representation of the mean borehole temperature. So instead of relying on a single depth, you can choose a range of depths over which the mean borehole temperature is computed. So this is an integration of the mean annual ground temperature across this defined interval. And the reason that this might be favorable to looking at ground temperature at one depth is that it's less susceptible to undetectable trends when the boreholes are near isothermal, so when ice is being lost in the ground. And it also makes boreholes more comparable as well if you choose to compare the same depth ranges. One of the limitations of the thermal integral is that it is more sensitive to interannual variability, and so you might need longer time series to really pick apart trends. And so, you could choose a range of sensors from 10 meters to 20 meters, but in our case, just based off of our data, we've chosen for the deeper sites to look at a range from 0 from about the ground surface to 10 meters deep, and for the shallow sites from the ground surface to about 3 meters deep. Our last metric, the metric number 5, is the depth of zero annual amplitude, which we've used in notation D subscript ZA. So you'll see that instead of the more common DZAA. And so this is not the temperature at this depth, but really how that depth fluctuates over time. And this metric is a proxy for latent heat in the ground, making it a really useful metric. Again, it is limited by the data available. So if sites or if boreholes don't extend deep enough and don't reach the depth of zero annual amplitude, then unfortunately this metric cannot be computed. Okay. Before I get into the actual observations, I wanted to present a case study just so everyone can kind of see how these metrics actually look when quantities are known, when the type of change in the ground is known. And so here I present a case study for simulated data at an ice-rich site where a warming trend was applied. And so this is over 7 years. So every profile is 10 years from its last one. And so the first year is in blue, and then the last year is in red. And you can look at how this progresses over time. And so on the x-axis here, you have temperature, whereas depth is on the y-axis. So if you're looking at mean annual ground temperature, you would see about 10 meters, you'd notice that, well, over time, the ground temperature has warmed. You can see it goes from about, a negative 1.5 degrees to about negative 5.5 degrees. Similar is observed at the surface. Mean annual ground surface temperature is also increasing. If we look at the depth of zero annual amplitude, you'll notice, so this is where these envelopes come together, so you're not getting that seasonal fluctuation. And so you'll notice that in the earlier years, in the early stages of thaw, you'll have an increase in the depth of zero annual amplitude. It shallows, and then it'll plateau during isothermal thaw, and then it deepens in the late stages of thaw. And you might have seen this simplified figure on the right here in like a physics textbook during high school, which just shows how a solid material or ice responds to the addition of heat, where you have temperature rising, and then during the mixed state phase where solid is changing to ice and latent heat takes over, you have this change of state, and you're not going to observe a change in temperature. And once it becomes liquid again, you get that change in temperature. Of course, this is simplified in the ground. There's mixed properties. There can be solids in the water or in the ice and all these things. But this is just to say that this is the depth of zero annual amplitude mirrors changes to latent heat in the ground. If we look at the region near 0 degrees, we can learn a little bit about permafrost. And so now we're looking, the solid lines are the net maximum temperature curve or temperature profile. And you'll notice that in the early years in blue, the top of permafrost is not changing too much. And then as time goes on and as this thaw is happening, the top of permafrost is being lowered deep into the ground. In terms of the thermal integral, again, this is a mean borehole temperature. Here, it's a pretty simplistic case where over time you notice that every depth is warming. And so over time, the thermal integral would also be increasing. Now, these same metrics can be calculated for every borehole that we have. But today, I just wanted to show you a subset of these boreholes, looking at only those that have data that extend past 2018, and of course, only looking at the metrics where at least 5 years of data are available. So we compute metrics at every borehole, and then we use the Mann-Kendall trend test to identify if there is a significant monotonic trend, that is increasing or decreasing trend. Here, we're not so much interested in the magnitude of the trends. That could be interesting at a different time. But here, it's really to identify whether or not we are seeing significant changes in the metrics. So for the about 70 boreholes that I have here, I was able to compute these trends across each one of these metrics. And so every vertical line is a different borehole, and every horizontal bar is a different metric. And so what you'll notice is, there's a lot of orange on the screen. Orange and blue colors tell us that there is a significant monotonic trend. Orange would mean that it is pointing towards permafrost degradation, or I've chosen to call it thawing here, blue for freezing. If gray, then there's no significant change. And it's in a lot of cases, there's no data available. This is just because the borehole doesn't go deep enough, or there aren't sensors that are shallow enough, or there's too much missing data, and so a trend just can't be computed. So aside from, the white, what mostly stands out here is orange, where we see that Across most sites, there seems to be this indication of thaw. And at many sites, when there is at least one, if there's more than one significant metric, then they tend to corroborate each other. And so they offer similar insight into permafrost change. In the absence of a significant trend at one metric, for instance, if there isn't a significant trend in mean annual ground temperature, there's sometimes a significant trend in other metrics. And this is just to say that these metrics, they provide additional evidence of permafrost change and can be really useful when certain variables or certain values aren't available. It is possible, of course, for certain metric results to contradict each other. This is usually in the case when mean annual ground surface temperature and mean annual ground temperature are compared. And this is because mean annual ground surface temperature is more sensitive to changes at the surface and will show, can show quite different trends compared to those deeper in the soil column. If we are to summarize this across all of these sites, so this really is showing the same as before, but we're only interested in metrics with significant change, less those that haven't returned significant monotonic change. We can see again that across most of these boreholes, there is indication of permafrost thaw. Now, having more metrics doesn't mean that the thaw is worse at one site than the other. All it means is that there's more evidence of change. And where contradictory evidence may be presented, then maybe more attention should be paid at that one site to see, what exactly to pick apart what type of permafrost change is being observed. Additional metrics can also tell us about the type of permafrost change, where you might just see ground temperatures warming. This could tell you, that permafrost might change in the future. But if you see, a lowering of the top of permafrost combined with a significant change in the depth of zero annual amplitude, you might think that, hey, there's some ice being lost in the ground. Permafrost is thawing and there'll be impacts occurring here. It's of course important to note that the duration of the data can impact the trend results. And this is because certain metrics are more sensitive to short-term changes. And these metrics are mean annual ground surface temperature, the thermal integral, as well as the depth of zero annual amplitude. So at the top here, I've written in the sites that only have 5 years of data, which is the vast majority of them. And then we have some that have more than 15 years of data. So there is this big difference here. And one thing that's important to note here is that there are, of the total number of metrics, those that only have 5 years of data have a lot fewer significant trends. And so this is probably because of these changes to sensitivity over the shorter time periods. Now, if there is no trend observed at a site, that doesn't mean, or no significant trend, that doesn't mean that change isn't being observed. It could be for a number of reasons. It could be just because of the short-term variability in the site. It could be because there's only 5 years of data, and the first one was right after drilling, and so there was disturbance in that first year. And so it's really important to be cautious with interpreting these results, but just to say that overall, the different metrics provide different avenues, different insight, and all together can tell you a little bit more about permafrost change. I want to now focus on one individual site that has shown multiple significant trends across the different metrics, and so where all of these trends indicate thawing permafrost or permafrost degradation. And so this site is named WJD02. And I'll first talk you through the metric results before telling you a little bit more about the site. And so here you see that mean annual ground temperature as well as mean annual ground surface temperature are increasing over time. Because of this, you would likely expect that the thermal integral, so this mean borehole summary, would also be increasing. And in fact, this is what's observed. So over time, you're also getting greater temperatures over time. And you'll also notice that the thermal integral, the temperature range is near 0 degrees. So it changes from about -1 degrees to 0 degrees over the measurement period. So with this, you might expect that some of these sensors are no longer within the permafrost layer. And so you'd expect there to be a lowering of the top of. So here, the line that I have shown here is dotted, and this is because the trend was not significant. But what you will notice is that in 2022, there is this drastic lowering of the top of permafrost. And this isn't an artifact of the data. It does seem to show this lowering. And so with, this lowering may not be significant, but seeing here as well as increases in temperature across the soil profile, In the presence of ice and ice-rich ground, you would expect there to be a significant change in the depth of the zero annual amplitude. And this is what is shown here, where you see an increase in the depth of the zero annual amplitude. And so this site is located in coastal Labrador. It's a borehole that's drilled into a small pulsa. And there's been a publication by Wang in 2024 that discussed some of these changes at different sites that they had in coastal Labrador. And at this site in particular, they observed about half a meter of subsidence from 2014 to 2023 caused by the loss of ice in the pulsa. So now if we, just take this one case study and scale it up to all of Canada, this figure shows similar summaries as what I just showed, but now I'm including the location of these boreholes, as well as the type of environments in which they're found. And so again, looking at disturbed versus undisturbed areas. And you'll notice that whether it's a triangle or a circle, disturbed or not, there is, permafrost change that's being observed. Now, I've chosen not to include the magnitude of change here. So here we're really using these metrics as evidence of thaw or lack of evidence of thaw, or even evidence of freezing. And I didn't want to show the magnitude trend for a couple of reasons. Well, first, because I wanted to maximize the number of sites that I'm showing here. Comparing trends is difficult when you have different measurement intervals. It's also, as I said before, complicated by the different site-specific characteristics and ice contents that then influence the magnitudes of the trend. The magnitude of the depth of zero annual amplitude, for instance, is also less important than just knowing that there is a change in the depth of zero annual amplitude. Another reason that we're not showing magnitudes of trends is, like I said, we really just want to show where we're observing permafrost degradation here. And so across most of these sites, you are seeing this orange color. And this is not to say that if the symbols are larger or smaller, meaning that there's more significant metric trends, that they should be, if there's fewer significant metric trends, then they're less important, or if there's no trends detected, then they're less important. But it can tell you where, efforts should be placed and which sites should maybe be a little bit more investigated to figure out, what's going on at that site, where we're seeing thaw, and what are the potential impacts of this change. So really to summarize and leave you some key takeaways, mean annual ground temperature sensitivity is reduced near 0 degrees. And so useful for maybe Canada-wide climate assessments, but less useful when you want to understand permafrost thaw. Using only mean annual ground temperature in reports leads to the over-reliance on one sensor and reduces the amount of data that we can use. Although metrics can tell us about thaw, it's important to keep in the back of our mind that they are sensitive to the duration of the data. And so it would be nice in the future to see how these look with longer time series. Some of the benefits of these metrics are that they allow for boreholes to be more comparable across different sites. For instance, the thermal integral, if choosing a common range for the thermal integral, these sites can be compared. And lastly, additional metrics, they provide evidence of thaw, but they can tell you a little bit more about the type of permafrost change that's observed than the standard approach. So the depth of zero annual amplitude tells you a little bit more about latent heat and the changes to the ice content in the ground, whereas ground temperature warming can tell you a little bit more just about permafrost degradation at a site. Thank you so much for listening. And thank you again to all the data contributors.
Thank you for that very interesting presentation. I'd like to open the floor up to questions. All right, Joe, you have your hand up. Go ahead.
Thanks, Olivia. It was nice to see your work and how it's developing. And I'm going to ask like a really selfish modeler question. I'd love to use this to compare our model against because it's very helpful when we have a lot of data like this. Is it possible to download this data like as a collection somewhere? Like, will that be your end result, or are you able to distribute this data?
Yeah, thanks, Joe. So the plan is to have not necessarily like a database, but at least an information sheet that can point you towards the direction of this data and possibly have not the raw data in this final data publication, but the modifications that I made. I had to go in and clean sites or flag certain sites where I thought that, strange things were happening. And so that is a final goal. Most of this data is already available online, and I'm happy to point you to the direction. I would say 95% of the data is available. A couple of sites have updated data that aren't published yet, but they are planning to be published in the near future.
Yeah, I think the biggest thing from perspective of someone like me, maybe it's just a laziness thing, is yeah, like if it's all in one spot, harmonized, like you've done, like cleaned, all that kind of stuff, then it's really valuable because when you compare a model, comparing a model at a single borehole is like, that's nice, you get the result and you just kind of shrug your shoulders. But if you have like 100 or whatever that you have, then it becomes really
Yeah,
valuable. We're looking at a lot of,
absolutely.
so okay, cool. Well,
Yeah,
anyway, but
thanks.
Hi, Olivia. It was a really nice presentation. I'm not able to turn on my camera because I don't have the camera. But my question is in regards to slide number 9. Yes. So it's very clear here that for some of the sites, the temperature is increasing with time.
Mm-hmm.
But does this take in effect the long-term drift of the sensors? And how does it take in effect the drift of the sensors?
That's a really good question. I don't believe the drift of the sensors is always discussed here. So I couldn't tell you, this isn't my figure. I know at other, yeah, I couldn't tell you right off the top of my head, unfortunately.
Thank you. Excellent presentation. Going to ask you a question that may be putting you in a spot. But in looking at the data, are you actually seeing trends that the active layer is thickening, deepening? It wasn't clear in the presentation whether you saw that. Certainly you're trying to calibrate analysis using as a reference point, but I'm curious if you're actually seeing, if the data is telling you that it's deepening.
Yeah, sorry, I didn't really focus too much on the trends. That is definitely an interesting thing, and I think something that people would want to know. So if you look at, so top, you can think of it right now as similar to the active layer thickness. And so if you look at this top panel here, in orange is where you are seeing this deepening of the active layer. And so across a lot of sites, you are seeing this lowering of the top of permafrost or the deepening of the active layer.
Wonderful. Thank you very much. Of interest to me as infrastructure. Thank you.
Mm-hmm. You're welcome.
Next, we have a question in the chat from Riley. Thanks you for a great presentation and is wondering if you can explain a bit more how you came up with your values for the thermal integral.
Yeah, absolutely. So I should say that I don't want to take anything away from the work that Nick has done, but I will happily explain it. Yeah, so what you would do is calculate the mean annual ground temperature across like a range of sensors. So starting at the ground surface, and then I would calculate mean annual ground temperature at every sensor down to, let's say, 10 meters deep, right? And then you would integrate those values across the range of depths. So you would integrate it, you would increase the value from 0 degrees down to 10 degrees, including all the ones in the middle. And so kind of taking that area under the curve, and then to make them comparable across sites, something that I didn't mention you do is that you normalize it by dividing the integrated value by the total range of depth. So from 0 to 10 meters, that would be, let's 10, you would divide by 10.
I just have a quick one, actually. Could you make any comment about the reliability of these metrics when it comes to, I guess, real versus simulated data?
Yeah, so in Nick's work, he really did try and mimic observed data, like little sensor inaccuracies. Non-stationarity is, of course, present in the data. He didn't, because it's simulated, you could in theory have, temperature at every like centimeter interval. But no, he chose sensor depths that are commonly observed and in fact that are recommended when installing sensors in the ground. As far as the reliability when comparing the metrics in the observed data versus, the simulated data, it is difficult just because he's working with, long time series. But they both struggle with they're both limited in similar ways in the fact that they are sensitive to short-term change. But otherwise, yeah, no, the methods that Nick used are trying to mimic observations as best as possible. Yeah.
Perfect. We have one last question in the chat. Terry is asking, can you speak to sensor drift?
Yeah, sensor drift. So it's tough because I don't have all of the information on what the data owners have done at their sites, how they calibrated their sensors, if they were recalibrated as they, went and downloaded the data, all this stuff. But when I first received the data, I went through like these rigorous process of like quality checking it, removing erroneous values and all this. And occasionally, at times you would see the sensor just drifting away. And the way that I checked out was just looking at, just sometimes it would be like a whole borehole that would drift, but oftentimes it's just one sensor that would drift. And so for those sites, I would then either remove that sensor and flag it in the final database. So that's how I dealt with sensor drift. But because I didn't install these sites, I can't speak more to how they were quality checked on their end.
Once again, thank you everyone for attending today's PermafrostNet seminar. Have a good day.